Hi, these notes have been made specifically for a small video, which is this video now, for using Euler's number. And Euler's number has to do with natural decay and natural growth. And we see this used in electronics extensively, and we'll be using it in our electronic fundamentals, used with capacitor circuits and used with inductor circuits, where we have what's called time constants. And we can look at the growth or the decay in voltage or in current to do with these capacitors and inductors. So I wasn't happy with some of the time constant curves that I found, including in some of the textbooks. So I've been meaning for a while to actually sit down and make my own one, and that's what I've done here. And I've used quite a few decimal places in these numbers, like, not just 0.63, 63%, but 0.6321206. And I've done that for a reason, because when we see the calculator that I'm using, I've used that many decimal places in the calculator. A, which is the blue curve here, is to do with, and this is all purely for capacitors, this particular video, capacitor voltage on charge. So the voltage is increasing exponentially, and that's called the first time constant, number one. Second time constant is here. Third time constant is here. Fourth is here at 98.16%. And really, most books, though, say that we consider capacitors fully charged after 5 time constants. But I mean, hey, look, even 3 time constants, it's at 95%. So, things really do slow down, as I said in the first video that I made about the capacitors. We're going to be using this letter E then, which is the universal constant for growth, and it's called Euler's number. And this is e to the minus x in our case, y equals e to the minus x. Now, I've got, I'll just plough down here, I've got a bit of a graphing software which is online, and I've already plotted this, y equals e to the x and y equals e to the minus x. Y equals e to the minus x represents this decay here, starting at a high number and coming down starting at a high number on the y-axis and coming down towards 0 on the y-axis. And y equals e to the minus x is, y equals e to the x is to do with growth. You can see we start at a low number on the y-axis and we progress up the y-axis to a higher number. And these other things that I've put here, well, let's look at this one first of all. Y equals e to the power of 1. Well, this really just shows us what Euler's constant or Euler's number is, which is 2.71828. And it's plotted on the graph by this line here. And if we go to the software and we expand the x-axis, we can see that number quite clearly plotted there. So y equals e to the minus 1, and we get a number 0.36787944. That number to us is going to be quite important in the study of capacitors. Doesn't look like a number that we've heard about talking about the growth in voltage so far, but we'll go to the calculations, and then I'll show you on the calculator what we can do with that number to make it into something more useful. I've got a small circuit on the time constant chart here showing a 1.8k resistor and a 47 microfarad capacitor. And we know that one time constant is going to be equal to the capacitance multiplied by the resistance in the circuit. So 47 microfarads, 1800 ohms, I've multiplied it out to get 84.6 milliseconds. What percentage of charge does this represent? Well, this is where this negative indice comes in, and it's e to the minus. And what I've done, I've taken one time constant divided by one time constant to get minus 1. So e to the minus 1, 0.3678. And that is that number that we saw here, 0.36787944. But after one time constant, we know that we're going to have a certain voltage across our capacitor. We're going to have a voltage developed across this capacitor after one time constant, and we've always learned that that's 63.2%. So how does this other number relate to 63.2%? Well, let's dive into the calculator and try that. I'll just clear the calculator, and I'll put in that minus 1 because that's what we had for the indice. So 1 minus, and then e raised to the power x, 0.3678794. But we need to subtract that from 1 to get the other number for growth, because this actually represents decay, as we'll find out momentarily. So to make that a number out of, to take that away from 1, the easiest way for me on this calculator is just to go minus in front and then add 1 to it, and bingo, 0.6321206. And that takes us back to the chart, 0.6321206. And that's that 0.632 number that we always talk about, 63.2%. So if I multiply that 63.2% times my rail voltage, now let's plow down here and just do some more work on that circuit. So if we've got 12 volts and we've got our capacitor, we've got our resistor, and we know that the time constant was 84.6 milliseconds. 6 milliseconds. And we said, find the capacitor voltage, and it'd be an instantaneous voltage at 84.6 milliseconds. Well, that happens to be one time constant. So as we saw, this is going to be, now let's just put this into perspective. This will be the V supply outside of brackets 1 minus E to the minus T over RC, because RC is our time constant, and minus time, so time divided by the time constant, all minus, and that'll be the index to which this is raised. So that becomes, in our case, 12 volts outside of 1 minus E to the minus 84.6. And that was what we did. And if I run the calculations on that, I now have to, we know that that was 63.2%, so we have to multiply that by 12 volts. So I'll just come back in here and multiply that by 12 volts, and that gives me 7.585 volts. And I'll just write that down then, 7.585. 7.585 volts. Too many things on the desk. 7.585 volts. I was right, wasn't it? 7.585 volts. Okay. Now, the interesting thing is that if we look at our chart, there's our 63.2%, and we had to multiply that by, because that's only a percentage of charge or discharge on this y-axis here, we multiplied that by our rail voltage. In this case, we've got 12 volts, and that gave us the 7.5 volts. But, if I take that 7.5 volts away from 12 volts. So if I go 12 minus 7.585 volts, and then I use that outside of 1 minus e to the minus 1, I'm also going to be then multiplying it by, so multiplying this difference between the 12, which is our final voltage, and the 7.585 volts, which was the first time constant. If I multiply that by 0.632xxxxx, and then I do some addition there, I'm going to come up with my second time constant. So this is why it's a natural growth and a natural decay. All right, let's have a look at doing that then. So that 12 minus 7.58, let's just do that on the calculator. So to make that, take all that away from 12, I need to really make that minus and then just add 12 to it. So I've got 4.414, and then if I multiply that by 0.632, what is it? Let's put some more digits in there. 0.6321206. 0.63212. That'll do. 0.63212 equals, and we get 2.7905. 2.7905. Wrong pen. 2.790 volts. And then if I add that voltage to the 7.5 volts that I've got there, I reckon I'm going to get about 10.37, are we? It's 557, yeah, 10.3755 volts. And then if I get that there as a percentage of 12 volts, so times 100, if I do that, 10.3755, 10.3755 divided by 12 equals 0.8646, 0.864625. 0.864625. And that number just happens to correspond to the next number in the series. So here it is here, 0.86466. I've got a rounding error because I didn't put enough digits in there. And then if we do the same thing, if we take that percentage of the 12 volts, subtract that from 12 volts, run 63.2% on that again, it'll just keep giving us the next number in the series, which will be 95% and then 98%, etc., etc. Okay. Now, I talked about this other software before, and I'll bring that up. Here it is here, Desmos.com. And this is quite interesting software. I've plotted y equals e to the x, which was the red graph here, y equals e to the minus x, which is the blue graph, y equals e to the minus 1 to give us that 0.3678 volts down here, and y equals e to the 1 to give us 2.718. And of course we learned that 0.367, we have to subtract that from 1 to get our growth number, which was 0.632. All right, let's go on then and have a look at using, with our little circuit here, we'll just do one more thing, and running out of time here, 15 minutes. I only wanted to make this a 5-minute video, but these things always take too long. Let's say, for argument's sake, we know that one time constant there was 84.6 milliseconds. So let's say we want to find the voltage there at 150 milliseconds. So that would be 12 outside of 1 minus e to the minus 150 divided by 84.6, close the brackets. All right, let's run the maths on that. 150 divided by 84.6. My calculator is a little bit like reverse Polish notation in a way. I've actually got RPN turned off, but the way this calculator works, I've got to start from the right-hand side of the equation. So 150 over 84.6. 150 divided by 84.6 equals sign change, e raised to that value, and then don't forget that's a decay value, so I need to find the voltage across the capacitor now, not the current in the circuit. So I'll have to subtract that from 1, which in my case the easiest way is to just make it a minus and then add 1 to it. So 0.8301, and then if I multiply that by 12 volts, bang, I'll get 9.96 volts. Equals 9.96 volts, and that is at 150 milliseconds in time from switch on. And you know, you can imagine there that if you look at the 5 time constants, if you got that 84.6 and you multiply that by 5 and you put that number over the top of the 84.6, make it minus, and you run the maths on that, you come out of that 11.999999999. And you actually, they call this an irrational number. You actually never actually get to the full value because I think Euler's number, they've worked out down to about 36 decimal places or something. Some incredible mathematical feat. Anyway, look, I'll wrap that up at that point. That was really all I wanted to show, just the use of E with being able to work out the voltage across a capacitor in an RC circuit. And of course, this other curve, just take a second to say this, as the voltage is increasing across the plates of the capacitor, the current in the circuit is decaying. And that's where those other numbers come in, the 0.36, the 0.135, the 0.018. So the current slowly goes back down to 0 as the voltage across the capacitor reaches the supply voltage over that 5 time constants. All right, I hope that was okay. It's very late at night to be doing a video like this, and I'm a little bit tired, but nevertheless, this is Greg Moore for TAFE New South Wales, and I hope that video helps you to answer some of the questions which you'll encounter in doing electronics study. Okay, bye for now.